Hello and thank you for clicking on this video by the Ipswich School Chemistry Society. Today we're going to be going over structure and bonding for the OCR Chemistry A-level specification. Our first thing to talk about is bonded pairs. So a bonded pair or electron pair is a shared pair of electrons within a covalently bonded molecule. So common molecules have anywhere from 2 to 6 bonded pairs, ranging from beryllium dihydride to sulfur hexafluoride. So bonded pairs repel each other equally within the molecule. Let's look at some examples. It must be noted before we look at some examples that double bonds behave like single bonds in terms of the shape of a molecule. Okay, so the first molecule we're going to look at is a linear molecule. This has 2 bonded pairs of electrons and a bond angle of 180 degrees. Two commonly occurring examples of this are beryllium dihydride and carbon dioxide. Our next molecule with 3 bonded pairs is a trigonal planar. This has a bond angle of 120 degrees, 3 bonded pairs as you can see. Commonly occurring examples of this are the carbonate ion, so CO3, and boron trifluoride. Our next molecule is the tetrahedral molecule with 4 bonded pairs of electrons. This has a bond angle of 109.5 degrees. Commonly occurring examples are the ammonium ion, NH4+, or CH4, the methane molecule. So our next molecule with 5 bonded pairs of electrons is trigonal bipyramidal. On the trigonal planar that you can see within this molecule, if I make it come up on the screen, there we go. The trigonal planar bond angle is 120 degrees, and the linear molecule slotted into the middle of it has a bond angle between the planar of 90 degrees. This isn't a very common shape and doesn't come up very often, but an example, if you need to know one, is phosphorus pentachloride. So our next shape is octahedral. This has 6 bonded pairs of electrons and a bond angle of 90 degrees. The most commonly referred to example of this is sulfur hexafluoride. So, on to lone pairs. A lone pair, or non-bonding pair of electrons, is quite self-explanatory. They are just a pair of unpaired electrons within the molecule that influence the shape. So, lone pairs are able to repel more strongly than bonded pairs. They often change the bond angle by about 2.5 degrees, but that is very variable. So let's look at some examples. So with 2 bonded pairs and 1 lone pair, we have the bent shape, or sometimes as it's known, the V shape. This has a bond angle of 118 degrees, and a commonly occurring example is tin chloride. It's not a very common shape, and it doesn't come up very often, but you do need to know it. And there is what it looks like. So, next we have 2 bonded pairs and 2 lone pairs. This is the bent molecule, something you'll be quite familiar with as it is the bonding of water. This has a bond angle of 104.5 degrees, and there you can see it. So our next molecule, which comes up quite often in past papers or may come up in your exam, is trigonal pyramidal molecule. This has 3 bonded pairs and 1 lone pair and has a bond angle of 107 degrees. A commonly occurring example is ammonia. So next we have the T-shaped molecule. This has 3 bonded pairs and 2 lone pairs and has a bond angle of 89 degrees, as we can see there. There aren't many examples of this. One example which has come up before is xenon trifluoride, which is an ion. Next we have the square pyramid molecule. This has 5 bonded pairs and 1 lone pair. There you can see it. It has a bond angle of 89 degrees, and a commonly occurring example is xenon oxyfluoride. So next we have 4 bonded pairs and 2 lone pairs. This is called a square planar. Again, it's not a particularly common molecule. It has a bond angle on the planar of 90 degrees, and between each side of the planar we have a bond angle of 180 degrees. A commonly occurring example is xenon tetrafluoride. So now we're going to address some oddities, because obviously not all molecules follow these rules. So boron and beryllium as elements do not have enough unpaired electrons in their outer shell to achieve noble gas configuration. Hence molecules, as we've seen earlier, like beryllium dihydride and boron trifluoride. Some elements are able to expand their octet, as we saw in phosphorus pentachloride. So elements further down in groups 15 to 17 have more electrons in their outer shell, which are able to take part in bonding. As a result, the atoms of the elements will often end up with more than 8 electrons in their outer shell. This is called expansion of the octet. So, elements able to expand their octet, in group 15, atoms of phosphorus and arsenic are able to form 3 or 5 covalent bonds. In group 16, atoms of sulfur, selenium or tellurium can form 2, 4 or 6 covalent bonds, and in group 17, atoms of chlorine, bromine or iodine and possibly acetine can form 1, 3, 5 or 7 covalent bonds. So let's look at an example. So here we have sulfur hexafluoride. This is an octahedral molecule with a bond angle of 90 degrees, and the sulfur atom within this molecule does have an expanded octet. So sulfur usually has 6 electrons in its outer shell, therefore it is able to take part in 6 covalent bonds as it does not obey the octet rule. So in sulfur hexafluoride, each of sulfur's outer shell electrons is paired, therefore it now has 12 electrons in its outer shell. Something to be noted though about sulfur hexafluoride is that fluorine is still obeying the octet rule. Thank you very much for watching our video on structure and bonding. If you liked the video, please like and subscribe. We'll try to make more videos like this.